Hi there, and welcome to the screencast on uncertainties and errors in measurement. This is a screencast in a series of screencasts on IB physics. This is topic 1 about physics and physical measurement. So in this screencast, we're talking about uncertainties, how to appreciate and understand them, and where they come from. What the uncertainties are when you're measuring on analog and digital instruments, how to minimize uncertainties. We'll learn about precision accuracy, random and systematic errors, how to combine uncertainties, and then how to represent uncertainties graphically. Let's get started. Well, errors and uncertainties happen, right? So this is a part of life, and we need to accept them rather than ignore them or what have you. So this is okay. So we need to be okay with uncertainties. In fact, IB really requires that we have uncertainties because they want to see if we can appreciate it and understand it. So every measurement, you're going to have some uncertainty. It's life. It's the real world. Why is that? Well, it could be the measuring device you're using. It's not very good. Could be the way you're measuring with it. Maybe you're doing something wrong or sloppy. Or the nature of the measurement itself. For example, the speed of light is really difficult to measure. So if you try and measure it with by however means, you're going to get some uncertainty in your result. So if you have an analog measuring device, and those are things that are, well, not anything that's non-digital. So for example, a watch, for example, or a clock that has the hands that are moving, in circular, on the circular dial. That's an analog clock. We're going to use plus or minus 1/2 the smallest scale division. Now this sounds a little confusing, but let's do an example. Okay, and this is going to be the best case. So if we have a ruler, this is an analog measuring device, right? And we have, let's say, right there. What would you say that value is? Would you say it's 4.2? And it looks like it's centimeters. What would be the uncertainty there? Well, according to this rule, we're going to take 1/2 the smallest scale division. So the smallest scale here, if this is 1 centimeter from 4 to 5, it's broken up into 10 divisions. So the smallest scale division here is 1/10 of a centimeter. And we're going to take 1/2 that. So 1/2 of 1/10, or 1/2 of 0.1, is plus or minus 0.05. So we would report this result to be 4.2 plus or minus 0.05 centimeters. All right? And we're going to always report our uncertainty to one significant figure in IB land. Okay. Another thing we're going to see is the number of decimal places need to be the same in both numbers. Now this is the best case, right? You would only go up from here. For example, if there were some other factors in your experiment that you thought made the uncertainty to be more than this, well, then you should go with that, right? Your opinion, your experimental technique, and your knowledge of it would trump this rule. So here's another example of an analog meter. It's a voltmeter. So any kind of meter with a needle that moves like this with a magnetic moment would be an analog meter. What would you say this value is right here? Well, I'll go ahead and pause your video if you want to take a stab at it. Okay, so the smallest division here looks like it's 1 volt, right? These are ones, it's 25. So 1 volt plus or minus 1/2 a volt. So we'd report this reading as 22 plus or minus 1/2 a volt. And here again, we want to have the same number of decimal places in our data value and uncertainty. And uncertainty to one significant figure. Let's try digital measuring devices. What's a digital? Well, these are meters that have like numbers flashing at you. And for these, we're going to use the smallest unit shown. That's also called the least count. For example, here's a digital voltmeter. And you can see this one is showing 19.16. So we're going to use an uncertainty of this decimal place over here, which is 0.01. So that's our uncertainty, plus or minus 0.01. Now, if you're taking measurements and you're doing the multiple trials, so you're taking the same exact measurement under the same conditions multiple times, we have a different way of calculating uncertainty. What we're going to do is find the average of all your trials when you do that. And the uncertainty is going to be 1/2 plus or minus 1/2 the range of your set of values. So you can have a maximum value for those trials, and you'll have a minimum. You take that range, and your uncertainty is plus or minus half of that range. Let's take an example of this. Say you go and measure a table, and you do it 5 times, and you get these results right here in millimeters. 1560, 65, 58, 67, 58. Well, the average value is 1563. We add them up, divide by 5, and we can find the average value. The uncertainty is we need to find the range, so we need to find the maximum. 67 looks like the biggest, and the smallest is 58. So we would subtract those two, find that range, divide by 2, you get 4.5 millimeters. So we report the length of the table to be our average, 1563, plus or minus, remember we must have one significant figure here, 5 millimeters. So this means that the true result could be anywhere within that range of 1558 to 68. Okay. Precision versus accuracy. What is that? Well, you might have seen this before, but they do have a meaning. Are they the same thing? No, they're not. So let's take an example here. We have a person, and we're going to measure his height using some kind of high-precision laser device. Right? All these measurements will be very similar, and the height was found to be, right, using the laser, 184.34 plus or minus 0.01 centimeters. Okay, since we have such a small uncertainty here, we can call this result very precise. That is, all the measurements we took were very close to the same number. Doesn't really matter what that number is, they're all the same. So we call that high precision. It's very precise. So multiple measurements, same results. Okay, so this is a precise result, but it's not accurate because the dude still has his shoes on over here, so that's not really his true height. So accuracy is how close the measurement is to its real value, its actually true value. So let's do this again. The guy takes his shoes off, and we measure his height, but we're going to measure it with a ruler this time. So the result is 181 centimeters and plus or minus 1 centimeter now. So we have, it's more accurate, that is, it's more near the true value, but it's less precise, right? Because we used an instrument that has less precision. So let's do this again, measure this fellow again without his shoes, and let's use the laser again. And now we're going to get some results that we have this here, 182.23, right? Multiple times, that's our average, and here's our uncertainty. So you can see that we have both precision and accuracy in this case. Graphically, right, we could represent accuracy and precision this way. So here we have, right, so you throw darts or you're shooting arrows, something, onto a target, and they're all kind of over in this area here. Well, how spread out they are is a measure of your precision, and how they are centered on the true measurement, which would be the bullseye here, is a measure of accuracy. So this one has got both high accuracy and high precision. Right? This one's got high accuracy. You're all around the true value, the bullseye, but you've got kind of these randomly errors over here. So if you kind of took the average of all these, it would kind of land in the bullseye. And this one over here, you bunched them up nicely, so you have high precision, but you're off a little bit. Maybe something is wrong. Maybe your sight is misaligned, or you're doing something wrong when you shoot every time. And lastly, here's one where we have an example of low precision and low accuracy. We can also represent that graphically this way. Right? This is your reference value here, and this is your distribution of your data. Right? How far away this peak is from your true value is your accuracy, and how wide this hill is here is a measure of your precision. Right? If they're all the same, you have a very steep peak right here. Okay, so let's talk about random errors. What are those? Okay, these are things you can't really control. These are normal variations in measurements. Like, for example, when you were shooting on the target, right, you had random errors there. If you have different people take measurements, well, that might produce some random errors. Somebody might read something different than you would. Right? A human reaction time. It's notoriously slow, and maybe you're a little sleepy, or maybe the other person had too much caffeine. Some kind of poor experimental technique. Okay, so we have to live with random errors. They're a part of everyday life, and we all can't afford the best measurement instruments, so we have to sometimes use a ruler or a stopwatch. But we can minimize these random errors by taking multiple trials and averaging the results. If those errors are truly random, right, then they should average away if we do it enough times. Systematic errors, however, is a different type of error. It's kind of like the fellow with his shoe on when we're measuring his height. Right? So this is a measurement that is off by some amount that's consistently bigger or smaller than the true value. And that would be like, for example, the guy with the shoe. His height was off by amount equal to the height of his heel on a shoe. In this case, for systematic errors, finding the average does not help us any because the measurement is off by the same amount every time. An example of this would be a zero error. That is, whatever meter you're using, when you disconnected, right, you don't start at zero. Like if you started measuring here at the end of the wood part instead of at the zero mark, that would produce an error in your measurements equal to this distance right here for every single measurement you made. And another example would be if you have a meter, that analog meter with a needle, if you disconnect it, is it really on zero? It should be. If it's not, you've got a systematic error. Okay, let's talk about ways you can state uncertainty. So remember we did the length of the table. We found the length to be this much here, 1563 millimeters plus or minus 5 millimeters. So we can say the absolute uncertainty is our 5 millimeters. We can also say that the fractional uncertainty is we take the 5 divided by our value here, and we get this fraction, or decimal, 3 over 1,000. The percentage uncertainty is you just multiply this fractional by 100, so we get 0.3% would be our percentage uncertainty. How to combine uncertainties? There are some rules for combining uncertainties. So for example, if you have an operation here, you're going to measure a bar here. You have a ruler and you have a bar and you want to say, well, how long is that bar? Well, you have this uncertainty from this is an analog, so we have plus or minus half the smallest, right, gradation here, which is 1/10 of a centimeter, so half of that is 0.05 centimeters. But we have that uncertainty at both ends, right? You have the uncertainty here when you start the measurement, and here also. So you really have twice that. So we could define and declare the total uncertainty for this length of this blue stick, whatever it is, to be plus or minus 0.1 centimeters. So we reported before 0.6 plus or minus 0.1 centimeters. Adding and subtracting. Okay, so we're going to add the absolute uncertainties when we have addition and subtracting. So for example, we have a basketball player is 196 plus or minus 1 centimeter, and you have another basketball player is 152 plus or minus 1 centimeter in height. What's the difference in their heights? Well, the difference is going to be, you just take the difference between these two values, 196 minus 152, you get 44. But we're going to add the uncertainties. Okay, so 1 and 1 gives us 2 centimeters. And you can think of this, right? If you have an uncertainty of 1 centimeter here, this guy could really be 197. And this guy could be 151. Right? In that case, the difference would be 46. And we could do that the other way too. So I think you might be able to see how it makes sense why we want to add those uncertainties when we're adding and subtracting. So let's do a different example. Have a block, and we want to find the volume of this block. The height, width, and depth all have an uncertainty of 1/10 of a centimeter. What's the uncertainty then in the volume of the block? So let's pick some numbers. That's probably the best way to illustrate it. So we have a height of 6 centimeters, width 10, and depth 5. Let's take this on the next page here, recopy that. So we can have a best estimate of the volume as the product of 10, 5, and 6. So multiply those together to get 300 cubic centimeters. That's our best estimate of the volume. But what about the uncertainty? Well, we know the uncertainty in the width. Right here, it's 0.1 divided by 10. That's 1%. The uncertainty in the depth is 0.1 over 5, which is 2%. The uncertainty in the height is 0.1 over 6, which would be 1.7%. So what we're going to do after we've converted all these uncertainties to percent is we're going to add those, and we get 4.7%. And we're going to report at 4.7% of our best guess as our uncertainty. So the volume is 300 plus or minus 14 cubic centimeters. Now this means it could be anywhere from 286 to 314, realistically. And one other thing to notice here, right? IB likes us to report one significant figure, so technically we should really report plus or minus 10 centimeters, cubic centimeters. Summarize when multiplying and dividing, right? We're going to add the percentage or fractional uncertainties of the quantities being multiplied or divided. Okay. The error bars, how to represent uncertainties when you have a graph or graphically? Well, we can do that. Right. So, for example, we have an x and y value here. This is our data, and we have an uncertainty of 0.1. So we could make a graph of that, and we make these error bars. They look like little i's, or maybe a big letter I, and a sideways letter I. This shows us the uncertainty, right? So this point really could be anywhere in this box. Now IB, when we do internal assessments, it only requires we do uncertainties or error bars for one of our variables, either this dependent or this independent variable. You should pick whichever one is worse. Okay, so let's talk about the slope. IB calls that the gradient. Okay, so we have a graph here, and we have a scattering of points. All right, so we want to plot the best fit straight line. Now, the best fit line in IB language could be a curve. A best fit straight line implies it's got to be literally a straight line. So we would do this. We could plot this, and we could do this by hand and get probably a reasonable estimate of the best fit straight line. But we could also use some software, right? Logger Pro will do this nicely for us, and so does your graphing calculator. You can do a linear regression, find the best fit line for your data. We can also have, in addition to our best fit line, we can have a minimum slope or minimum gradient. And the way we're going to find that is we take this first point, right? Go to the topmost error bar in that first point and the bottom error bar on the last point, and we're going to draw a line between those. And now we have this blue line has got a smaller slope or smaller gradient. That could be the minimum for this data set, since this point really could be up here based on our uncertainty, and this one really could be down here somewhere. So this is not necessarily the best and most perfect way to find minimum gradient, but it is one way. And this is what we're going to use. Same with the maximum gradient, right? We're going to find this bottommost error bar point and this topmost error bar point here, and we're going to draw a line between those two. So we actually going to have three lines on our graph. We can have a best fit slope, and we can have a maximum and minimum gradient. Now the gradient usually means something. It has some meaning. For example, if this was a distance or position, displacement, and time, right? So displacement and time, the slope of that graph would give us velocity. So the gradients here or slopes would represent velocity, and the difference between the maximum and minimum gradient here would give us our range of velocities based on our uncertainty and our measurements. Okay, that's it for this screencast. Bye.